Number 25. It says a recent study found that life expectancy of people living in Africa is normally distributed with an average of 53 years with a standard deviation of 7.5 years. We want to answer the following questions. If a person in Africa is randomly selected, A, what is the probability the person will die before the age of 65? Now, you do not have to draw the bell-shaped curve if you don't want to. I chose to draw the bell-shaped curve because it says the variable is normally distributed. Furthermore, it says a person in Africa, right? So when it says a person is selected at random, a person represents one person. Let's keep that in mind. So we know that the mean is 53. And the standard deviation is going to be 7.5. So the mean goes in the middle of the distribution, which is 53. The value that we're focusing on in this case is 65. So we can call that X. 65 falls on the right side of the mean. And because it says that the person will find a probability that they will die before the age of 65, we're going to shade that to the left. Make this a little bit smaller. Now remember, when the area is shaded to the left of the z-score, or the left of a value, the probability that we get will be used for our final answer. In our case, we don't have a z-score right now. We have to convert our raw data into a standardized score in order to find the probability. Because we're looking at one person, we will be using the z-score formula. Z is equal to the data value minus the mean divided by the standard deviation. So Z is equal to 65, which is the score under examination, or the age under examination, minus the mean of 53, divided by the standard deviation of 7.5. All z-scores should be rounded to two numbers after the decimal. Let's open up our calculator. So that's going to be 65 minus 53 on top. That gives you 12. Divide that by 7.5. That gives us 1.6. Now we're going to go on our table and find the probability that z equals to 1.6. Let's go into the standard normal distribution table. Make this a little bit bigger so we can reference. Okay. So it's a positive z-score. Let's go to the positive side. Positive 1.6. You know what? Let's make this like this. There we go. So that's going to be right here. Positive 1.60. Let's highlight it, make things better. So the probability of that z-score is 0.9452. And because the area is shaded to the left, this probability will be used for our final answer. So the probability that a person will die before the age of 65 is 0.9452. Or if you want to give a percentage, we can say that's 94.5%. Either one should suffice. Now, when it comes to B, it says, what is the probability that the person will die after the age of 65? So once again, the mean is 53. The standard deviation is 7.5. The score that we're focusing on is 65. You do not have to draw the bell-shaped curve if you don't want to, but I choose to do it to give a visual representation. Also, let me indicate that this means to the left. Let's box this. And because it says die after 65, that is going to be indicating of to the right. So we're going to shade to the right of 65. Remember, all probabilities on the normal distribution table is the area to the left of the z-score. When it's to the right of the z-score, you must subtract the probability from 1. So once again, we have to find the z-score. Z equals to 65 minus 53 divided by 7.5. We already know that z equals to 1.6 from before. We know the probability that z equals to 1.6 is 0.9452. But because the area is shaded to the right, you must subtract the probability from 1. The probability that a person will die after the age of 65 is 1 minus 0.9452. And this is going to equal to 0.0548. Or you can say roughly 5.5%. That is the answer to part B. Now, part C says, what is the probability that the person will die between the ages of 41 and 65? So when we're focusing on the probability between two values, we must find the z-score for both of those values, find the probability of each of those z-scores, then subtract the probabilities with the larger one being first minus the smaller one. So we have two values we're focusing on, 41 and 65. So we must find the z-scores for both of them. The mean is still 53. The standard deviation is still 7.5. So z equals to 41 minus 53 divided by 7.5. And then for this one, z equals to 65 minus 53 over 7.5, which we know the answer is z equals 1.6. And then the probability of that z-score is 0.9452. Let's do the math for this one. So that's going to be 41 minus 53. That's negative 12. Divide that by 7.5. We have negative 1.6. To find the probability that z equals negative 1.6, well, we should know that already. That's going to be 0.0548. But we can go onto our normal distribution table, go to the negative z-score side, negative 1.6, which is right here. And that's going to be 0.0548. Then to wrap this up, to find the probability that a person will die between the ages of 41 and 65, subtract the probabilities. 0.9452 minus 0.0548. Let's not do this in my head. And that's going to be 0.8904. Or as a percentage, you can say that's 89%. Okay, letter D. It says, if 1,000 people living in Africa are selected at random, how many of them do you expect to die after the age of 65? So we want to find, based on this sample size, or based on 1,000 people, which can be the population, which is not, of course. We want to see how many would we expect to die after the age of 65. We're going to use the expected value formula, but there's only one event that's going on. So E is going to equal to N times P. N is the sample size, P is the probability. Our sample size is 1,000 people. And the probability that a person will die after the age of 65 is 0.0548. Remember, we found this probability in part B. So to find the expected value, or the expected amount of people, let's multiply 1,000 times 0.0548. This is going to equal to 54.8. Because this is people, let's round this value up to 55. We expect 55 people to die after 65 years. That is the answer to D. Now, E. I'm going to do E in two different ways. Every professor has a different approach. So do I. So this one says for E, find P90, which separates the bottom 90% from the top 10%. This is also known as the 90th percentile. Okay, I want to focus on the bottom 90%. And the reason why I want to focus on the bottom 90% is because, remember, every probability on the standard normal distribution table is shaded to the left. And when we think about bottom, we should think about to the left. Now, look what I wrote here for the notes. P90 equals the age separating the bottom 90% from the top 10%. That means you have to find the value of X. You have to find that age that separates the bottom 90% from the top 10%. So I'm going to take this bell-shaped curve right here. Place 0 in the middle for my z-score. 90% is pretty big. So the bottom 90% and the top 10% should be divided somewhere around here. We need to find that z value. And I'm going to shade this region right here. Get that in a little bit better. There we go. And this is the bottom 90%. Or we can say that this is 0.9000. Because the percentage is a probability. 90% is 0.90. Just add 2 more zeros. To find the z-score, we have to find z first. we must go into the body of our standard normal distribution table in order to find the z-score. So I'm going to write here, find z that represents 0.9000 to the left. So let's open up our normal distribution table. And let's find the closest probability to 0.9000. So it's not going to be on the negative side. It's going to be on the positive side. And if we look, the closest probability that we can get to 0.9000 is 0.8997. And that z-score is positive 1.28. That's great. We have our z-score. So the z-score is positive 1.28. With that said, we now can solve for x. We can find that age that separates the bottom 90% from the top 10%. Now, some instructors use the regular z-score formula to solve for x. Some instructors, including myself, use way number 2, which is known as the raw score formula. So this is using z formula. This is using raw formula. Raw score formula. Okay, give a little bit of variety to both sides. So our z-score is 1.28. So 1.28 is going to equal to x, which is unknown for right now, minus the mean of 53, divided by the standard deviation of 7.5. Now, we want to multiply both sides by 7.5 in order to get rid of the fraction. These simplify. So let's see what is 1.28 times 7.5. That's 9.6 equals to x minus 53. Then you can add 53 to both sides. X equals 62.6. So we found P90. P90 is 62.6. Now, if you use the raw score formula, it's just an easier way to plug things in, which is for way number 2. X is equal to the z-score of 1.28 times the standard deviation of 7.5 plus the mean of 53. We can plug that into the calculator like we did here. 1.28 times 7.5 plus 53. We get 62.6, which is still P90. And just to wrap up this video, if you're in my class, you may have an additional resource that you could potentially use on the final, depending on how I feel. This document is known as the z-table for percentages and critical values. Now, it does make question E kind of easier to answer because you can easily find the z-score. So remember, bottom 90% from the top 10%. If you go here to top 10%, that z-score is positive 1.28. Or furthermore, because it says this is known as the 90th percentile, if you scroll down, the z-score for the 90th percentile is positive 1.28. Therefore, you don't have to necessarily use the standard normal distribution table in order to find the z-score. But like I said, it just depends. So yep, that is it for part E. Let's scroll down to part F. F says, if a sample of 36 people living in Africa are selected randomly, find the probability that the sample mean is after the age of 65. Use the standard error of the mean if the finite population correction factor is ignored. Okay, because we're looking at a sample of 36 people, and the variable is normally distributed because it says it in the beginning, but also because the sample size is 30 or more, we will be using the central limit theorem in order to find the probability. It says the sample mean is after the age of 65, which means we're shading to the right. So, we know that the population mean is 53. We know that the standard deviation is 7.5. This time, we have 36 people we're looking at. And the sample mean will be after the age of 65. Let's use the central limit theorem z-score formula. Z equals to 65 minus 53 divided by the standard deviation of 7.5 divided by the square root of 36. That's 12 on top. That is going to be 1.25 on the bottom. If I'm doing my math correct, we can always double check. So 7.5 divided by the square root 7.5 of 36. Yep, 1.25. 12 divided by 1.25. That is 9.6. Now let's find the probability that z equals 9.6. There is no z-score of 9.6 on this table, but there is a key indicator that lets us know what to do. For z values greater than 3.49, use 0.9999. So we're going to do that. So this is 0.9999. But because the area is shaded to the right, we must subtract this probability from 1. So probability that the sample mean is greater than 65. That's 1 minus 0.9999, which is going to be 0.0001. And that is the answer to this question. And that is it. That is it for question number 25. Hope that made sense. Hope you enjoyed the video. And I'll catch you in the next one. Take care.